Welcome to the Deep Dive, the show where we slice through the endless stream of information, bringing you crystal clear insights on topics that shape our world. Our daily lives are just a constant bombardment of data, from the sounds in our environment to the signals our own bodies produce. But how do we actually take that raw, often chaotic data, especially in critical fields like medicine, and transform it into crucial, clear signals that we can understand and act upon? This isn't just like a technical challenge, it's pretty fundamental to modern life. Today, we're embarking on a deep dive into the fascinating and honestly absolutely indispensable world of FIR filters, that's finite impulse response filters. And we're going to shine a particular spotlight on one of their most powerful and essential characteristics, linear phase. Our mission today is to truly unpack what these filters are, how they meticulously work, and why their unique ability to maintain linear phase isn't just some technical footnote. It's really a foundational cornerstone for accuracy, reliability, and ultimately trust. This characteristic is particularly vital in sensitive areas like biomedical signal processing, where the integrity of a waveform can literally be, well, a matter of life and death. We're drawing our insights from foundational texts in the field, including biomedical digital signal processing and design of FIR filters, to bring you the core understanding. So get ready to look at the world around you a little differently. This deep dive is designed to sort of shortcut you to being genuinely well-informed about a topic that underpins so much modern technology, from the precision of life-saving medical imaging to, the pristine audio systems you enjoy every single day. Let's start by laying the groundwork. Okay, let's unpack this. We often hear the term filter in everyday contexts: your water filter, the air filter, even social media filters. But when we talk about filtering signals, what does digital actually mean here? What's the fundamental shift from, say, an old-school analog radio?
That's a really crucial distinction. Digital filters are, in essence, the discrete domain counterparts of traditional analog filters. Think of them as the modern evolution, really, designed for a digital world. Analog filters, like in those old radios, rely on physical electronic circuits, resistors, capacitors, inductors that directly manipulate continuous electrical waveforms. They operate on a smooth, uninterrupted flow of electricity.
Right, a constantly changing voltage.
Exactly. Digital filters, however, take a fundamentally different approach. Instead of those continuous waveforms, they operate on a sequence of numbers. These numbers are obtained by sampling the continuous waveform at regular intervals, essentially taking snapshots thousands or millions of times a second.
Okay.
So a digital filter is implemented not with physical electronic components changing voltage directly, but through digital logic circuits, or much more commonly these days, computer programs. It's software or specialized digital hardware working with a stream of data points.
So if I'm picturing a smooth, continuous sound wave, the digital filter isn't like touching the wave itself, it's taking measurements
Thousands of tiny measurements
of that wave every second.
Yeah.
And then doing math on those numbers.
Yeah.
Kind of like a super fast connect the dots, but with calculations.
Precisely. You're capturing the essence of the signal as a series of discrete numerical values. And this digital approach brings some really significant advantages. First, they have a high immunity to noise. Because the signal is represented by numbers, definite values, rather than those fluctuating voltages, it's far less susceptible to electromagnetic interference or other kinds of analog corruption.
Makes sense. It's clearer, less fuzzy.
Right. The data is either a specific number, not some voltage level that can drift. Secondly, their accuracy is remarkably high. It's determined only by the round-off error that happens when you represent numbers with a finite number of bits. But, and this is key, this is something designers directly control. They choose the number of bits used for representing variables. More bits mean more numerical accuracy, allowing for incredibly precise filtering operations that would be, frankly, almost impossible to achieve reliably with analog components. That precision and noise immunity are real game changers.
That makes the shift to digital seem almost inevitable for anything requiring high precision. So if we want to build any digital filter, no matter how complex, what are the absolute basic operations, the fundamental building blocks?
Yeah, you've hit on a critical point there. Regardless of the complexity, any digital filter can be constructed using just 3 fundamental operations. Think of them as the atomic elements of digital signal processing. The first is storage, which basically means delaying a number for a specific precise interval, usually 1 clock period. In the mathematical language we use, the Z-transform, this operation is represented very elegantly by Z1.
Okay, so Z1 just means delay by 1 time step. Can you give me a more sort of concrete image of how that works? If a new data point comes in, what happens?
Absolutely. Imagine a conveyor belt for numbers synchronized by a clock. If a number, let's call it x0, enters at time t0, this storage element holds onto it for exactly one clock cycle. Then when the next number, xt, enters at tt, where t is your sampling period, the time between those snapshots, x0, is simultaneously pushed out to the output.
Oh,
The net effect is that your output sequence is simply your input sequence, but delayed by exactly t seconds. The very first output when x0 enters is usually initialized to 0, then it outputs x0 when xt enters, xtt when x2t enters, and so on. It's basically a precisely timed memory cell.
got it. So delay or storage is building block 1. What's number 2?
The second fundamental operation is multiplication by a constant. This is just scaling a number. You take an input number, multiply it by some fixed value, and you get an output number instantaneously, at least in theory. For instance, if you have a sequence of numbers like 5, 9, 0, 6, and you multiply each by a constant, say 5, the output is an instantaneous 25, 45, 0, 30. There's no inherent delay modeled in this operation itself.
Right, just scaling. And the third?
The third is addition. Just like multiplication, this operation involves summing numbers, maybe from two different sequences, or summing the results of several multiplications, perhaps. Again, in the ideal model, this operation is considered instantaneous. So with just those three actions, delaying, scaling, and adding, you can construct filters of incredible sophistication.
Wow, just those three.
Just those three. And to tie this back to the real world, think about a microcomputer, which is often the brain of these systems. It performs these functions easily. Its memory acts as the storage element, holding data points. And the computer's CPU, the central processing unit, is perfectly suited for essentially instantaneous multiplication and addition. But crucially, the key to timing control, the whole orchestration of the filter, lies entirely with those storage elements, the Z1 delays. The multipliers and adders are ideally assumed to have 0 delay. It's the precisely controlled delays that make the whole thing work.
Okay, so with those fundamental building blocks, delay, multiply, add understood, let's turn our attention to the star of today's deep dive, the FIR filter. You mentioned the finite part of its name is a big clue. Why is finite so important here?
The significance of finite is truly profound. An FIR filter is defined by having a unit impulse response that has a limited number of terms. It eventually goes to 0 and stays there. This stands in direct contrast to infinite impulse response, or IIR, filters. With IIRs, if you put in a single pulse, a unit impulse, you theoretically get an infinite number of non-zero output terms trailing off.
Okay, so FIR stops, IIR keeps going.
In essence, yes. And the core reason for this difference in FIR filters is that there's no feedback involved in computing the output. The output depends only on the present input sample and a finite number of past input samples. This lack of feedback is precisely what makes FIR filters inherently stable, always. Any transients, any weird starting conditions, they will always eventually die away completely. You don't have to worry about an FIR filter suddenly spiraling into uncontrolled oscillations or ringing indefinitely, which can happen with IR filters if they aren't designed carefully. FIRs are completely predictable in that sense.
That inherent stability and predictability sounds like a massive advantage. I mean, if you're dealing with, say, a medical device monitoring a heart, the absolute last thing you want is your filter becoming unstable and spitting out garbage data, or worse.
Exactly. That reliability is paramount.
So how do we actually visualize or mathematically describe what's happening inside one of these stable FIR filters? What do the equations look like?
A really direct way to visualize it is using a signal flow graph. Picture a chain of these storage registers, our Z1 delay elements lined up. Each one holds a previous input sample. The input signal comes in at one end, and it shifts down the line step by step, getting delayed at each register. We call these points taps.
Taps, okay.
Yeah. And the filter's output at any given moment is simply the weighted sum of the values currently sitting in those registers at those taps. Each value is multiplied by a specific tap weight or coefficient, and then all those weighted values are added together. Mathematically, this behavior is captured perfectly by a difference equation. Y(n)t) equals sum bkx ntkt for k going from 0 up to n.
Okay, let's break that down a bit.
Sure. Y(nt) is your current output sample at time nt. The x and tkt terms are your past input samples specifically. The input sample from k, time steps ago, delayed by at seconds.
Right, the ones held in those registers.
Exactly. And the bk values, those are our tap weights or filter coefficients. They're the fixed constants that each delayed input sample, x and tkt, gets multiplied by before they all get summed up to produce the current output, yn and t. It's a direct feed-forward calculation, no loops.
And this difference equation, I assume it translates directly into that z-domain transfer function you mentioned, which gives maybe an even clearer picture of the filter's structure.
Absolutely. The transfer function in the z-domain is a really powerful mathematical representation that clearly shows the finite nature. It looks like this. Hz equals b0 plus b1z dash plus b2z dash 2 plus... So this equation makes it totally explicit that the filter's output depends on a finite number of delayed input terms. You see z sine 1, z took 2, up to z and n. Those are the delay elements. It's a polynomial in z1 of finite degree, n, hence finite impulse response. And here's a particularly neat and insightful point. The unit impulse response of an FIR filter is equal to its tap weights.
Wait, really? So if you poke it with a single pulse?
The sequence of numbers that comes out is precisely the sequence of coefficients, b0, b1, b2, bn, boom. That direct one-to-one relationship simplifies analysis and design hugely compared to IR filters, where the impulse response is infinite, related to the coefficients in a more complicated way because of the feedback.
Wow. Okay. So with FIRs, the coefficients basically are the filter's fundamental response. That's elegant. So we've got stability lockdown as a huge benefit of FIR filters. But now let's zero in on this other critical characteristic you mentioned, the one that really elevates FIR filters for so many precise applications: linear phase. You use the music analogy, bass arriving later than drums. It makes sense that timing matters. Can you expand on why this is so critical, especially in, say, medical signals?
That music analogy really hits the nail on the head. The issue of phase distortion is particularly acute. It demands meticulous attention in many biomedical signal processing areas. Take an ECG, an electrocardiogram. Preserving the original shape of that waveform is absolutely paramount. Think about the QRS pulse, that main sharp spike that visually signals a heartbeat. Its height, its duration, even its precise morphology. The subtle bumps and slopes carry crucial diagnostic information.
Right. Doctors learn to read those shapes very carefully.
Exactly. Now, if a filter introduces phase distortion, it means different frequency components within that single QRS complex get delayed by different amounts of time as they pass through the filter. This messes up their relative timing. It effectively smears or reshapes the entire pulse. The signal's appearance changes, maybe subtly, maybe drastically, and with that change in shape, potentially its clinical meaning changes too.
Yikes. So you could misinterpret something purely because the filter warped the signal's timing.
Precisely. You might mistake a normal variation for an anomaly, or worse, miss a subtle sign of a problem, simply because the filter distorted the signal's fundamental shape by messing with the timing relationships between its frequency components.
So what exactly is linear phase then, in practical terms? How does it prevent this timing mess-up?
Okay, so filter has linear phase if its phase response amounts to just a pure time delay. This is the ideal scenario. It means that all frequency components that pass through the filter are delayed by the exact same constant amount of time.
Ah, okay. Everything shifts together.
Everything shifts together, exactly. Their relative timing is perfectly preserved. And because of that, the original waveform shape remains absolutely intact. If you put a perfect square wave in, you get a perfect square wave out, just shifted slightly later in time. You don't get a distorted, rounded, or tilted version.
That sounds incredibly valuable. How do we define that mathematically?
Mathematically, we say a filter has linear phase if its frequency response, H, can be written in a very specific form. H10 ACO plus 0. Now, H1 here is a real function, maybe positive or negative, but it only affects the amplitude of each frequency, not its timing relative to others. The crucial part is the ACO plus 0 term. That represents the linear phase component. This mathematical structure guarantees that the group delay, which is basically the average delay experienced by a narrow band of frequencies, is constant across all frequencies in the passband. It's this constant group delay that prevents different frequencies from being delayed by different amounts, thus protecting the waveform's shape.
This really does sound like a superpower for signal integrity. And this is one of the biggest reasons FIR filters are the go-to choice then. This ability to easily achieve linear phase.
Absolutely. It's arguably one of their most defining advantages, especially over IIR filters, where achieving linear phase is much, much harder, often impossible without tricks. The key mechanism: FIR filters achieve linear phase relatively easily through specific kinds of symmetry in their impulse response, their coefficients. You can have even symmetry, BK, BNK, or odd symmetry, BK, Rayukale, combined with whether the filter length n+1 is even or odd.
Symmetry in the coefficient.
Yes, this internal symmetry is much easier to impose and control in FIR filters because, unlike IIRs, they don't have those complex feedback paths that inherently introduce tricky, nonlinear phase distortions. When you look at the math for a symmetric impulse response, where the coefficients are mirrored around the center, like B0 matches Bn, B1 matches Bn1, and so on the frequency response, hxpgj simplifies beautifully. It becomes a purely real function, essentially a sum of cosine terms, multiplied by a simple linear phase term. 2xpj B0 cos m2 plus B1 cos m2 plus where m is n.
Okay, that exponential term looks like the delay part.
Exactly. That xpj2 directly translates to a pure constant delay of m2 samples, which is exactly half the filter length. Antisymmetric impulse responses also yield linear phase, just with a slightly different constant phase offset. But the critical part is the linearity of the phase with respect to frequency, ensuring all frequencies get the same time delay.
So linear phase is fantastic, preserves the shape, major win for FIR. But, there's rarely a free lunch in engineering, right? Are there trade-offs? Does this linear phase requirement cost us anything?
You're absolutely right. There are always trade-offs to consider. One primary consideration is the filter's length, or order. Generally speaking, linear phase FIR filters tend to be longer, meaning they require a higher filter order N and thus more coefficients, more memory, more taps compared to nonlinear phase filters like IIRs or even non-symmetric FIRs, designed to meet the same frequency response specifications like the same cutoff sharpness or stop band attenuation.
So potentially more computation needed.
Intuitively, yes, more taps usually means more multiplications and additions. However, here's where it gets really interesting, a kind of clever optimization. This increased length doesn't necessarily translate into being significantly more computationally intensive. Symmetric FIR filters can be implemented using a very neat trick called a folded delay line structure. Because the coefficients are symmetric, BK, BNK, you don't actually need to perform two separate multiplications for BK, XNK and BNK, XN, NK.
Oh, so
you can add the corresponding input samples first, add XNK and XNK together, and then multiply that single sum by the shared coefficient buck. This simple pre-addition trick significantly reduces the number of multiplications needed.
Oh, clever.
Yeah, it typically halves the number of multipliers required, down to about n2 or n plus 1, 2 instead of n. So a longer symmetric linear phase FIR filter can often be just as computationally efficient, sometimes even more efficient in terms of multiplications, than a shorter nonlinear phase 1 or a comparable IIR filter. You get that crucial benefit of perfect phase preservation, often without a major hit in processing demands.
That's a fantastic piece of engineering efficiency. And just to clarify, one point is linear phase always critical across the entire frequency spectrum.
Yeah.
Even for the frequencies we're trying to get rid of in the stop band.
That's a really important practical point. No, not always. Linear phase in the filter stop bands, the frequencies you're actively trying to attenuate or block, is rarely a critical requirement. If those frequency components are being heavily suppressed anyway, their relative phase relationships usually don't matter much to the final output signal. The primary concern, almost always, is the integrity of the signal within the passband, the frequencies you want to keep and analyze. That's where preserving the waveform shape is typically paramount, especially in sensitive applications like biomedical signals. So design efforts usually focus on ensuring excellent linearity in the passband, while the phase response in the stop band might be allowed to be nonlinear without causing issues.
Okay, so we definitely appreciate the value of stable, linear phase FIR filters now. But the big question remains. How do we actually design them? How do we figure out those magic BIC coefficients to get the specific filtering job done? You mentioned it starts with an ideal concept, one that's not actually buildable.
Exactly. That's the fundamental challenge of filter design, bridging the gap between an ideal, perfect theoretical filter and something you can actually implement in hardware or software. Let's take the ideal low-pass filter again. Theoretically, it's perfect. Its frequency response is exactly 1 in the pass band, passes everything perfectly and precisely, 0 in the stop band, blocks everything completely. And crucially, the transition between pass and stop is an infinitely sharp vertical drop, a perfect brick wall.
Sounds great. Why can't we just build that?
Well, the problem lies in its impulse response. To get that perfect brick wall in frequency, the impulse response you need is the sync function, HDN, where ek is the cutoff frequency. Two major problems here. First, this function is infinitely long. It stretches out forever in both positive and negative time. You'd need an infinite number of coefficients, infinite memory, infinite delay. clearly impossible.
Right, impractical.
And second, it's non-causal. See how it extends into negative time n? That means to calculate the filter output now, you'd need to know input values from the future.
Okay, definitely can't do that.
Yeah.
Unless you have a time machine.
Exactly. So while the ideal filter is a nice mathematical concept, it's physically unrealizable.
So to make it real, we have to somehow chop off that infinite response and make it causal, make it work only with past and present inputs. This is where the idea of a window comes in, isn't it? Like looking at only a finite piece of that infinite ideal response.
Precisely. The simplest, most intuitive way to approximate the ideal filter is to just take a finite segment of that ideal impulse response. We truncate it. We say, okay, let's use the ideal HDN values only for n within a certain range, maybe from L to plus L, and set all the values outside that range to 0. This effectively cuts off the infinite tails of the sinc function. Then, to make it causal, we shift this entire finite segment to the right along the time axis, usually by m12 samples, where m is the total length of our chosen segment, so m equals 2l plus 1 if centered initially. Now, it only depends on past and present inputs, and here's a really powerful mathematical connection. This truncation operation is mathematically identical to multiplying the original ideal infinite impulse response by a rectangular window function in the time domain.
A rectangular window, like a function that's just 1 for the duration we want to keep and 0 everywhere else.
Exactly that, just a flat top pulse. You multiply the infinite sinc by this rectangle. Seems simple, but this act of multiplication in the time domain has profound and often undesirable consequences in the frequency domain.
Ah, the trade-offs again. What are those profound and undesirable implications? What happens to our nice ideal brick wall when we multiply by that rectangle?
Well, several things happen due to a fundamental property of Fourier transforms. Multiplication in one domain, time, corresponds to convolution in the other domain, frequency. So the actual frequency response of our truncated windowed filter is no longer the ideal brick wall. Instead, it becomes the convolution of that ideal brick wall with the frequency response of the rectangular window itself.
Convolution.
Yeah.
It sounds like it smears things out.
It does exactly that. This convolution smears the sharp edges of the ideal response. Firstly, it introduces oscillations or ripples in both the pass band, where we wanted a flat 1, and the stop band, where we wanted a flat 0. This is the famous Gibbs phenomenon. The sharp edges of the rectangular window in time cause this energy spreading in frequency, leading to these persistent wiggles. And here's the kicker. The amplitude of the main ripples near the cutoff frequency does not decrease as you make the filter longer, increase m. They just get squeezed closer together.
Oh, so making the filter longer doesn't make the ripples smaller. That seems like a problem.
It's a major limitation of the simple rectangular window, yes. Secondly, the transition bandwidth changes. The transition from pass band to stop band is no longer infinitely sharp. It becomes gradual. The width of this transition region is directly related to the width of the main lobe of the rectangular window's frequency response. And thirdly, there's the delay. As we saw mathematically before, the frequency response of the rectangular window itself, W, inherently includes a linear phase term E, GOM12. So the good news is this simple windowing process automatically preserves the linear phase characteristic we want, introducing a predictable delay of M12 samples.
Okay, so rectangular window gives linear phase but has nasty ripples that don't go away and a non-ideal transition. Surely engineers have come up with better windows, ones that don't have these sharp edges in time.
Oh, absolutely. Decades of work have gone into developing alternative window functions precisely to mitigate the problems of the rectangular window, especially that stubborn Gibbs phenomenon ripple. There's a whole family of them. Hanning, Hamming, Blackman, Kaiser, triangular, Chebyshev, Gaussian. Lots of choices.
What's the general idea behind these other windows?
The core idea is to taper the window function smoothly down to 0 at the edges, instead of the abrupt cutoff of the rectangular window. Imagine multiplying the ideal impulse response not by a sharp rectangle, but by a function that starts at 0, smoothly rises to 1 in the middle, and then smoothly tapers back down to 0 at the ends. This smoother tapering in the time domain dramatically reduces the ripples, side lobes, in the frequency domain. However, it comes at a cost. Each window offers a distinct trade-off between two key parameters. One is the main lobe width. A wider main lobe in the window's frequency response generally leads to a wider, less sharp transition band in the final filter. The other is the sideband ripple, or stop band attenuation. This measures how much the ripples in the stop band are suppressed relative to the pass band gain. Better ripple suppression usually means a wider main lobe.
Can you give an example of that trade-off?
Sure. The rectangular window has the narrowest possible main lobe for a given length m, with about 4m, giving the sharpest potential transition. But its side lobes are terrible, only about negative 13 dBs down. Not much attenuation. A Hanning or Hamming window uses a cosine-based taper. They have significantly better side lobe attenuation, down to negative 31 dB, Hanning, or even minus 41 dB, Hamming, meaning much less ripple, but their main lobes are roughly twice as wide, about 8 bem, so the filter transition band will be wider, less steep. A Blackman window tapers even more smoothly, achieving excellent side lobe attenuation, negative 58 dB, but its main lobe is wider still, about 12 m.
So it's always a balance between sharpness and ripple.
Exactly. And then you have windows like the Kaiser window, which is really clever. It has an adjustable parameter, usually called 8-beta, that allows the designer to explicitly control this trade-off. You can tune dib to get precisely the amount of stop band attenuation you need, accepting the corresponding main lobe width, or vice versa. It offers much more flexibility.
So designing with windows sounds like you'd probably try a few things. Pick a window, pick a length, see if it meets spec, and if not, tweak it.
That's exactly how it often works in practice. It's an iterative process. You define your desired passband ripple, stop band attenuation, and transition width. You make an initial guess for the filter length M and choose a window type, maybe Kaiser, because it's tunable. You calculate the coefficients, check the resulting frequency response. If it doesn't meet the spec, say the transition is too wide, you might increase M or adjust the Kaiser back. If the ripple is too high, you might need a window with better attenuation, and likely increase M to compensate for the wider main lobe. A big advantage is that this method easily generates linear phase filters just by ensuring the windowing maintains the symmetry of the ideal impulse response segment. The main drawback. Window design is relatively simple, but generally not optimal. It usually results in a filter that's longer, higher order N, than theoretically necessary to meet the specs.
Okay. So beyond this general windowing method, are there other, maybe more specialized ways to design FIR filters for particular jobs?
Yes, indeed. Once you grasp the windowing concept, you can explore more tailored approaches. Let's touch on a few important ones. First, there are smoothing filters. Their main goal is pretty straightforward: reduce high-frequency noise. This noise can come from all sorts of places. 60 hertz hum from power lines, muscle twitches in a physiological signal, movement artifacts, even the small errors introduced when converting an analog signal to digital quantization error. The simplest smoothing filter is just a moving average. You average, say, the last 3 or 5 data points. This inherently smooths things out, acting as a basic low-pass filter. The Hanning filter we mentioned is a specific type of weighted moving average. For more sophisticated smoothing, you can use polynomial smoothing filters. Instead of just averaging, these try to fit a low-order polynomial like a line or a parabola to a small window of data points, and the filter output is the value of that polynomial at the center point. The order of the polynomial affects how aggressively it smooths.
What if you have a very specific frequency you need to kill, like that exact 60 hertz hum? Smoothing might reduce it, but maybe not eliminate it entirely.
Excellent point. For that kind of pinpoint frequency removal, you need a notch filter. Its whole purpose is to completely obliterate noise at one particular, very narrow frequency band while leaving nearby frequencies largely untouched. The magic here involves using the Z-transform again. You strategically place a zero of the filter's transfer function directly on the unit circle in the Z-plane at the precise angle corresponding to the frequency you want to eliminate.
A zero on the unit circle. What does that mean practically?
Think of the unit circle in the complex Z-plane as a map of frequencies from 0 up to half the sampling rate. Placing a mathematical 0 at a specific point on that circle forces the filter's frequency response, its gain, to be exactly 0 at that specific frequency. It's like creating a perfect cancellation, a black hole, just for that one frequency. For instance, if your sampling rate is, say, 180 samples per second, and you want to kill 60 hertz noise, which is 13 of the sampling rate, corresponding to an angle of 2-3 radians or 120 degrees, you'd place zeros at Z as X or XP J23, that's Z equals 0.5 plus J.866, and Z equals 0.5 J.866. This can sometimes result in a very simple FIR filter. A common 60 Hz notch filter, for instance, might just involve averaging the current sample with the sample from 2 steps ago, YNT 0.5 XNT plus XNT to T, or even simpler, a 3-point average like YNT plus XNTT plus XNTTT can also create notches, depending on the sampling rate.
That's incredibly targeted. Are there methods that work directly in the frequency domain from the start, instead of starting with an ideal time response and windowing it?
Yes, that leads us to the frequency sampling method. This approach can be more direct than windowing. Instead of designing in the time domain via the impulse response, you directly specify the filter's desired frequency response, HO, at a set of n equally spaced frequency points around the unit circle. You basically say, I want the gain to be 1 at these frequencies, 0 at those frequencies, and maybe something in between at others. The filter coefficients are then calculated using the inverse discrete Fourier transform, essentially, to match those frequency samples exactly.
What are the pros and cons there?
The big advantage is that it guarantees your filter's frequency response will hit precisely the values you specified at those chosen frequency points. The main drawback is that you don't have direct control over the filter's response between those points. This can lead to significant ripples or overshoots, especially if you specify a very sharp transition between passband and stopband points. You can mitigate this somewhat by leaving the frequency samples in the transition band unspecified or unconstrained, giving the algorithm some freedom there. Generally, frequency sampling can produce more efficient filters, lower order for similar specs than the window method, but the fine control over the response shape is trickier.
Okay, so windowing is simple but suboptimal. Frequency sampling is direct but can have ripple issues between points. What's considered the sort of gold standard for optimal FIR filter design, especially when you need the absolute best performance for a given filter length.
That would generally be minimax design, also commonly known as equiripple design, often implemented using the Barks-McClellan algorithm or the Remez exchange algorithm. Unlike methods that try to minimize the average error or the sum of squared errors, like least squares, Minimax takes a different philosophy. It aims to minimize the maximum absolute error between the desired frequency response and the actual filter response across the specified frequency bands, passband and stopband.
Minimize the maximum error. What does that result in?
It results in a filter where the error ripple has equal amplitude across the entire passband, and similarly, equal amplitude ripple across the entire startband, hence the name equiripple. It effectively spreads the error out as evenly as possible. This method is mathematically much more complex and computationally intensive to implement than window design. It involves iterative optimization algorithms. However, the payoff is often significant. Minimax design typically yields the lowest possible filter order n for a given set of specifications: passband ripple, stopband attenuation, transition widths.
So it's harder work, but you get a more efficient filter.
Exactly. You might find, for example, that to meet certain specs, a window design requires N80 coefficients, while a Minimax design achieves the same performance with only N33. That's a huge saving in computation and memory in the final implementation. These algorithms also allow designers to apply different weighting to the errors in the passband versus the stopband, giving very fine control over the trade-offs to precisely match the application's needs. It's the most powerful tool for designing truly optimal linear phase FIR filters.
Right, so we've covered the theory, the crucial linear phase aspect in these various design techniques. Let's bring it back to the real world, especially those high-stakes environments like medical devices. What does all this mean when you're processing signals, say, from a patient in an ICU, where everything has to happen now?
This is really where FIR filters, particularly linear phase ones, become not just useful, but often a genuine necessity. Think about that ICU computer monitoring an ECG. It's acquiring data constantly, point by point. In these situations, processing has to happen in real time. That's not just a nice to have, it's a hard constraint. Every single incoming data point needs to be filtered, analyzed, and potentially trigger an alarm before the next data point even arrives milliseconds later. There's no time to wait, no buffering up chunks of data for later processing. It's immediate, continuous, and critical.
That sounds like a massive computational burden, especially if the device is running on a relatively low-power microprocessor, not a supercomputer. How do they handle the math, those multiplications and additions, fast enough?
That is a huge challenge. Standard digital filter equations, as we've seen, often involve coefficients that are floating point numbers, like 0.31415. Performing floating point multiplication can be relatively slow and power-hungry on many microprocessors, especially older or simpler embedded ones. This can easily become the bottleneck, preventing real-time performance.
So how do engineers get around that?
They often turn to a clever variation: integer filters. These are digital filters specifically designed so that all their coefficients, bk, are integers, or sometimes simple fractions that can be represented easily using integers. Why does this help? Because integer multiplication is generally much faster on most processors than floating point multiplication. Even better, if you can constrain your integer coefficients to be powers of 2, or sums of powers of 2, you can replace multiplication entirely with extremely fast bit shift and add instructions.
Ah, like multiplying by 8 is just shifting the binary number left by 3 bits.
Exactly. Shifting bits is one of the fastest operations a processor can do. By designing the filter carefully using integer coefficients, especially powers of 2, you can dramatically cut down the computation time for each output sample. This is often the key trick to achieving that necessary real-time performance on resource-constrained hardware.
That's a very neat optimization for speed. But does limiting yourself to integer coefficients impose constraints? Does it make it harder to design a good filter?
It certainly can, yes. There's a trade-off. While integer filters are much faster, you lose some design flexibility. It can be harder to achieve extremely sharp cutoff frequencies or very deep stopband attenuation when you're restricted to integer coefficients compared to having the full range of floating point values available. You have to find integer values that approximate the ideal coefficients well enough. Sometimes the performance might not be quite as good as a floating point design, but the speed advantage is often critical and makes it the necessary choice for real-time systems where good enough filtering done instantly is better than perfect filtering done too late. And importantly for our theme today, it's crucial to remember that even order integer FIR filters, where n is odd, meaning m plus 1 coefficients is even, can still be designed to have perfect linear phase, just like their floating point cousins, often by using symmetric integer coefficients. Odd-order integer filters can sometimes have phase issues, like 180-degree jumps, so careful design regarding symmetry and order is still needed.
Let's make this really concrete. Can you walk us through a classic life-saving example where FIR filters, linear phase, and real-time processing are all essential? Maybe that ECG QRS detection you mentioned earlier, finding the heartbeat spike.
Absolutely, that's a perfect case study. A really influential and widely used method is the Pan-Tompkins algorithm, first published back in 1985. It's designed specifically for reliable real-time QRS detection, and it brilliantly uses a sequence of FIR-based filtering and processing steps to pick out that crucial heartbeat signal from all the noise.
Okay, so what are the steps? How do FIR filters help find that QRS spike?
It's a clever cascade of stages. First, the raw ECG signal typically goes through a bandpass filter. This is a crucial FIR filter designed to maximize the energy of the QRS complex while attenuating noise outside its typical frequency range. The QRS itself has most of its energy roughly between 5 Hz and 15 Hz. So the bandpass filter is designed to let these frequencies through while significantly cutting down lower frequencies like baseline wander from breathing and higher frequencies like muscle noise or 60 Hz hum if it wasn't notched out earlier. It isolates the signal components that look most like a heartbeat.
So step 1 is isolate the likely frequencies. What's next?
Next comes differentiation. The algorithm uses a simple, efficient FIR derivative filter, often just a few taps long, like a 5-point filter. Why differentiation? Because the QRS complex is characterized by its sharp slopes, rapid changes in voltage. Differentiation enhances these slopes, effectively acting like a high-pass filter. It amplifies the high-frequency components associated with the sharp QRS upstroke and downstroke, while suppressing the lower-frequency, slower waves like the P wave before the QRS and the T wave after the QRS. This makes the QRS stand out even more.
Okay, bandpass, then derivative to emphasize the sharpness.
Then there's a squaring operation. The output of the derivative filter is squared point by point. This does two things. First, it makes all the data points positive, which simplifies later processing. Second, squaring nonlinearly amplifies the larger signal values, so the already enhanced QRS peaks become even more prominent compared to any remaining noise or smaller waves.
Got it. Positive and emphasized. What's the final filtering step?
The final main step is a moving window integrator. This is, again, another FIR filter, essentially a moving average filter applied to the squared signal. It sums up the energy in the squared signal over a specific time window, often chosen to be around the typical width of a QRS complex, maybe 150 milliseconds. This integration acts as a smoothing, low-pass filter. It produces a feature waveform where each point represents the energy in the preceding window. The result is a much smoother signal with broad peaks corresponding to each QRS complex, making it relatively easy for a simple thresholding mechanism to detect when a heartbeat has occurred. And regarding that initial bandpass filter, there's a subtle but important design choice related to its Q factor, or quality factor. That's the center frequency divided by the bandwidth. If you make the Q too high, meaning the filter is very sharply tuned, it can become overly oscillatory. It might ring after being excited by a QRS complex.
Ring, like ripples after the main event.
Exactly. These ripples must die down quickly, typically within about 200 milliseconds, so they don't interfere with the detection of the next heartbeat. So you have to choose a Q value, often around 1 to 5, that's high enough to give good noise rejection, but low enough to prevent excessive ringing. It's another optimization balancing act.
And when they actually build this into a portable heart monitor or something, do they use those integer filter tricks we talked about?
Very often, yes. Especially for the derivative and integrator stages, which can often be implemented with very simple coefficients. For instance, that 5-point derivative might use coefficients like 1, 2, 0, negative 2, minus 1, may be scaled by 18. Using 18 instead of a precise gain like 0.1 allows that division to be done with a super-fast 3-bit right shift. Similarly, the moving window integrator involves summing and sometimes dividing. These operations can often be implemented very efficiently using integer arithmetic and bit shifts, which is critical for getting that real-time performance on potentially low-power embedded processors inside the medical device.
It's really incredible how these layers of mathematical concepts and clever engineering tricks come together in devices that are literally saving lives. It's not just abstract theory at all.
Not at all. It's deeply practical applied engineering. And the ability to do this kind of sophisticated signal processing has been utterly transformed by advances in integrated circuit technology, especially VLSI, very large-scale integration. What might have required a whole rack of equipment decades ago can now be implemented on a single, tiny, low-power chip. This miniaturization and efficiency increase has enabled the proliferation of complex signal processing in everything from medical devices to smartphones. And this has also driven the development of digital signal processors, DSPs. These are specialized microprocessors architected from the ground up, specifically for the kinds of calculations needed in digital filtering and other signal processing tasks. Think of families like the Texas Instruments TMS320 series, or the NXP, formerly Motorola, DST-56000
Yeah,
family.
so these DSP chips are basically optimized for those three core operations.
Yeah.
Delay, multiply, add.
Exactly. Their internal architectures are heavily optimized for that. They often use techniques like parallel processing, doing multiple calculations at once, pipelining, overlapping the execution stages of instructions, and having dedicated hardware multipliers and accumulators. They leverage concepts like multiprocessing, systolic arrays for data flow, RISC, reduced instruction set computer principles for speed, all geared towards achieving extremely high computational throughput for real-time signal processing. A key performance metric for comparing DSPs is often their MA time, the time it takes to perform one multiply and accumulate operation, which is the absolute core calculation in FIR and IR filtering. The faster the MAC, the more complex the filtering you can do in real time. This relentless progress in hardware continues to push what's possible with FIR filters. Hashtag outro.
Wow. What a truly deep dive that was.
Right.
We've really journeyed from the absolute fundamentals, those basic building blocks of delay, multiplication, addition, right through to the incredible stability, and crucially, the waveform preserve and precision of FIR filters, all thanks to that linear phase characteristic. We've seen how engineers use these ingenious design techniques, from the straightforwardness of windowing to the optimality minimax methods to actually craft these filters, and often using those clever computational shortcuts like integer filters to make them run incredibly fast in real time. And we've seen their absolutely vital role in applications like, well, reliably picking out the rhythm of a human heartbeat from all the surrounding noise. It's amazing.
It really is. It makes you appreciate the layers of hidden complexity in the technology we rely on. And it also raises some interesting questions looking forward, doesn't it? As computing power just keeps growing exponentially and our understanding of complex signals, especially biological ones, gets deeper, what new frontiers will open up? What will even more sophisticated, more efficient FIR filter designs allow us to see or detect? Think about the subtle details currently buried deep in noise, maybe early indicators of disease that future filters might be able to cleanly extract. The potential is enormous.
That's a fascinating thought, what new signals might emerge from the noise. It's a constant quest for clarity. So next time you hear that perfectly clear audio from your headphones, or maybe see a sharp, detailed medical image that helps a doctor make a diagnosis, maybe take just a second to consider the unseen layers of FIR filtering humming away in the background. These elegant mathematical tools, these FIR filters with their linear phase, they aren't just abstract concepts in a textbook. They are the invisible architects constantly working to shape our understanding of the complex signals that define our world and, in many cases, our health. They bring clarity out of chaos.